I'm Jordi Blasco from HPCNow, and today I'm going to give you a quick overview about the solution I developed for monitoring efficiency of jobs. First, I'm going to introduce myself. I'm Jordi Blasco, I'm CTO at HPCNow, and my background is in computational physics. As you know, a computational physicist is a scientist that has a formal education in physics, but also knows quite a lot about math and computer science. This fits in the classical representation of expert in everything and good at nothing. I have been playing different roles from HPC end user support and system administration to computational scientist and solutions architect. I have been working in public institutions, national level HPC facilities like the Supercomputing Center of Catalonia, based in Spain, or NESI, the National HPC Facility based in New Zealand. More recently, I jumped to the other side of the fence. I co-founded HPCNow with some ex-colleagues in late 2012, which started to get into real business around 2014. HPCNow is a global consulting company focused in HPC. All the people working in HPCNow has a very similar background and career path. Half of the team are computational scientists, the other half are computer engineers. Some of us actually have both degrees at the same time. So, tell you a little bit more about HPCNow. We don't sell hardware. Actually, we are software and hardware agnostics. We are basically a service company, which complements really well with most of the popular hardware vendors. This also includes consulting services for planning or solution design, installation covering from the hardware infrastructure to the software, including key components like cluster managers, cluster file system, workload managers. But because we are also scientists, we are able to install and tune scientific applications. We provide training from very traditional HPC system administration to parallel programming, performance analysis, or AI workflow engines with Kubernetes. And finally, we also provide managed services. We provide reactive support for HPC system administrators and end users, and also managed services. In this scenario, we take basically care of all the computational services, and the clients can focus on the core of their business. Going back to the topic of today, I'm going to talk about job efficiency monitoring, more specifically on the solution that we design and develop in order to improve our managed services. As you know, identifying efficiency issues is very time consuming. I started to develop this tool in order to accelerate the time to solution and identify opportunities to improve efficiency and the performance of the clusters. So the motivation around this is very simple. So as a consulting company like HPCNow, it means a lot. If we can accelerate the time we spend on identifying those issues and we can spend more time actually solving them, it gives us the ability to provide a better response and better services. So what we want is to basically detect those issues really quickly and add more value to our services. Thanks to this tool, we are able to reinvest our time in achieving better utilization of the cluster, spend time in code and application tuning, improve user workflows, or increase the user education by delivering training events, workshops, and one-on-one sessions. We also realized that this tool has been really useful to quantify the impact of our work. Now we can assess how much capacity we have been able to return to the end users, or how much speed up we have been able to achieve after tuning each application. So the tool that I'm going to introduce now, it has been developed to accelerate the way we deliver our services. The main objectives are discovering really quickly the potential issues, ideally a way earlier than the final user, or before an operational workload gets compromised. Identify tuning opportunities to improve either user codes, applications, or workflows. Increase the return of investment by tuning the workload manager policies and introducing mechanisms to increase the effective utilization of the cluster. And finally, being able to accelerate the client's business. So the traditional mechanism for accelerating the research in a supercomputing facility is usually by a bigger and faster cluster. More recently, using cloud services as a part of cloud bursting, it's an ongoing strategy. Unfortunately, those two options have some drawbacks. Buying a new cluster, usually it involves a really complex procurement process. And in addition to that, not all the supercomputing facilities have a well-consolidated platform refresh cycle. In addition to that, for using the cloud, you have to take into account many things. How much data, how many data you need to stage in and out. Are the codes really suitable for the infrastructure that you have available in the cloud? How long it's going to render? Small jobs, usually you want to keep it locally in order to improve backfilling. Long-term jobs, usually it's quite very costly to run in the cloud. You want to keep it locally. So those kind of business rules you need to massage, and we do that for some customers, but it's not the regular approach when you are talking about a generic kind of facility. So what we are doing now here, and thanks to the solution that I'm going to introduce you, we have been able to improve the efficiency. So somehow it's a way to create more allocation for new jobs. And this comes with a zero investment in a hardware capacity. So the limitations of the traditional technologies, as you probably are aware of, like Ganglia Manning or Zabbix, is that they are not capable to represent the efficiency issues of the jobs. Those tools are basically monitoring the load of the cluster. As you're going to see in a few minutes, the cluster could be working at 100% of the CPU capacity and being not very efficient at the same time. So those tools have no link to a user, no link to a job, no link to other nodes allocated for the same job, and definitely has no information about the efficiency. So in terms of a wish list, in terms of requirements that we define when we started, is to be able to identify opportunities to improve user workflows, user codes, applications, and definitely being able to identify user mistakes. So what we want is to track all the metrics that define the usage of the cluster and compare them with the resources actually requested by every single job. The mismatch between them is what we want to represent as well. And if it goes over a certain threshold, we can trigger an alert. Another thing that we want to see is real-time monitoring. There's no point on having those statistics once the job is completed, especially for very long-term jobs. And then in terms of resolution, so the expectation was to get up to 30 seconds resolution, which is kind of a reasonable resolution for a majority of HPC workloads. But nowadays, we have been able to go down to up to 10 seconds resolution. Let's move on the architecture. Because of the large number of events to be analyzed, we have to use big data strategy. So that's why we are using InfluxDB, and Elasticsearch as databases. And then we represent the data with really nice dashboards in Grafana. This diagram represents an overview of the complete solution. At this time, we support traditional HPC environments based on InfiniBand and also supercomputers based on Aries Interconnect. In terms of storage, we currently support IBM Spectrum Scale, GPFS, Lustre, and BGFS. In this box over here, we have all the components that we need in order to make this solution to work. We have 3 Elasticsearch instances distributed across different physical nodes, 2 HA proxies for load balancing, then Bits, Logstash, and Kibana for the log representation and events representation, collectd for aggregating metrics from the compute nodes, OGRT for getting more details about the applications and commands run inside the jobs, and then InfluxDB as a database, Grafana as a dashboard engine, and Isinga for alert system. The topic of today basically is targeting Elasticsearch. It's targeting collectd, InfluxDB, and Grafana. As you can see here, the way we implement the solution is it relies on Docker, on container orchestration. So we currently support a Swarm and Docker Swarm and Kubernetes. So this has been key for us to accelerate the way we deploy the solution really quickly, and we can replicate the same installation everywhere we go, every client that we have, the managed services, and we have exactly the same end user experience. So far, we have been able to achieve the following key features: a quick discovery and fast analysis of potential issues. It has been an incredible flexible tool, able to visualize the data that the customer is interested in. It has demonstrated to be a scalable solution and really cheap to scale. And it took a while to organize everything, but now we are able to orchestrate the complete software stack in almost no time. And the part that I'm most proud of is that it has a very low footprint, either at the memory level and at the CPU level. We have conducted some benchmarks in 240 nodes running HPL, and we haven't been able to identify performance difference between them. I'm going to give you an overview of some of the dashboards that we have already developed. As you're going to see in the next few minutes, this tool helps to understand the real needs and the user community trends. While this tool was initially developed for the end user support teams and for computational scientists, it has been able to provide also very useful information for platforms team and end users. Okay, so this is how it looks, the job efficiency monitoring dashboard. In this case, I'm representing data coming from Slurm. In this case, this graphic here highlights the amount of CPUs under use by every single user in the cluster. Obviously, I'm just highlighting here the top 10 users. And as you can see here, there's one particular user that has been able to underuse up to 1,600 CPUs over this period of time. This graphic shows data from 7 days, last 7 days. And over this period of time, this particular user has been able to manage to underuse more than 7.5 years of CPU time. Well, this is just for the CPU resources. Identifying CPU efficiency issues is actually quite easy because you can evaluate the CPU utilization real time. In the case of the memory, things are a little bit different. We have to evaluate this at the very end of the job, once the job is completed. Could be a situation where memory requested by the job is actually going to be used at the very end of the workflow. That's why in this case, we are evaluating the memory usage, the mismatch between the memory usage and the memory requested at the very end. In this case, we can see few users requesting a way more memory than they are actually using. So up to 1 terabyte of memory allocated is wasted because of that. So this is per job. Then in this one, we can see the aggregated underused memory. As you can see here, it's several hundreds of terabytes of memory allocated but not in use over this period of time. We're talking 7 days. In this graphic down here, we can see an overview of the resources requested, highlighted in red color, and resources in real use. So the gap between those two lines is actually the resources not in use. And then in this graphic here, we can see the average of a CPU efficiency. And as you know, the average hides a lot of information. So if you have kind of a HTC and HPC environment, and the HTC workloads are very inefficient, so this will reduce the efficiency to a really high level. Let's have a look how it works. The dashboard allows you to filter per user. So I can just select here a particular user that we want to explore, or increase the time frame that we want to explore. And as you can see here, we have seen in this particular case up to 4,000 CPUs under use over this period of time. Now, looking for a specific user, we can see the metrics coming only for that particular user. As you can see here, the mismatch between the resources requested and the resources actually in use is quite huge. So we are talking about 1,510 CPUs requested, but then only 15 are in use. This is how it looks, the Slurm accounting and job distribution. So in this table here, we can see the accumulated CPU time provided to each individual. In this other table here, usually we see the CPU time in use per account. It's just that this client only has one account. Everything gets accumulated into the root account. And in this graphic here, we can see something really interesting. It's the job distribution. With the job distribution, we can see the patterns in the user community and for each individual as well. As you can see here, I can filter just for a particular user, and I can see the job distribution for a particular user. In this axis, we can see the job size, and in the x-axis, we can see the elapsed time. The color of each dot represents the frequency. And as we can see here, there's a high frequency of jobs requesting around 960 cores and around 190 or 180 hours of wall time. So this information, for example, could be very useful. So this, in this case, it's just a snapshot because we are talking about just 30 days. But imagine that this is the situation that you see as well after 1 or 2 years of having this tool running and collecting data. If you see a job distribution like this, and you see that the biggest number of jobs running the cluster are more or less this size, then you are in a better position to evaluate if there's a real need for having a non-blocking InfiniBand, or if you could do exactly the same kind of job and still being able to meet the user needs with a blocking factor 2 or a blocking factor 4 and reuse this budget in having more compute capacity, for example, or other features. In this graphic, we can see the aggregated CPU time per job state. In this particular case, we can see that 49% of the CPU time delivered by this cluster has been successfully completed. There is less than 1% that actually fail because of a hardware or software failures. The rest of the CPU time is actually lost because of a human error. As you can see here, around 43% of the CPU time is lost because the jobs got an underestimated wall time. And another 5% of the jobs got cancelled for any other reasons. In the next graphic, we can see exactly the same information, but rather than representing the CPU time, it represents the number of jobs. The interesting lecture here is that only the 1% of the jobs, it actually crashed because of a timeout, underestimated timeout. This means that the jobs with this underestimated wall time must be quite parallel. Finally, we represent the CPU time loss per user. This helps us to identify who actually needs more help. I would like to highlight a couple of things here. So please note that in a situation like this, traditional tools like Ganglia, Manning, or Zabbix may report a high load in the CPU of the cluster. But in reality, half of the CPU time is wasted for any of those reasons. The following dashboard represents key metrics of the workload manager. In this case, Slurm. The metrics represented here helps to identify potential trends in the HPC users and identify two new opportunities in the scheduler policies and limits. This is how it looks the cluster status. The metrics exposed here are targeting user satisfaction. As you can see here, the average waiting time is quite long, and the cluster global efficiency is quite low. In this particular case, there was a cluster hogging issue, quite a terrible one. Few users were requesting quite uneven resources, in particular, quite a lot of memory per core. This made the cluster unable to satisfy common needs. This dashboard represents the most recent features incorporated in the development of this tool. In this dashboard, we can see the number of CPUs under use per user and a table of jobs running over a particular time window. We can select an individual user or a job and explore the behavior. In the table, we have a very basic information about the job, and the job ID is actually a link to a proactive job profiling dashboard, as you can see here. The proactive job profiling dashboard provides an overview of the resources used real time, basic information of the job, and the job script used to submit the job. Now, if you think about the steps that you have to take in order to get this data, you can see how much time we save. If a user complains about efficiency issues in the job, usually you need to identify the job ID, SSH into the cluster, escalate to root privileges, navigate in the cryptic home directory of the user, try to find the submit script, and while you are doing all those things, you hope that the user still keeps a copy of the submit script somewhere. When you finally understand what the script is trying to do, you need to submit again the job with some instrumentation. Wait for the job to get started, collect the data once the job ends, visualize the data, and finally is when you're going to start to do the valuable work, which is analyzing the data and trying to fix the issue. You may think that the data I use for this demo has been selected to highlight the worst case scenario. Unfortunately, we have seen very similar issues in several environments. Well, finally, conclusions. So we were looking for a tool to increase scalability, performance, and efficiency. Those are basically the three things that you want to achieve in a standard HPC facility, right? But having this capability has been able to detect user mistakes, increase the HPC user maturity, and also quantify the impact of our services in client sites. And that's the end. Thank you so much for attending this talk. And please, if you have any question, ask away. Thank you.